Hello, Math 1224. This is Dr. P with Lesson Launch 603. You might be wondering about the title of this video. I'm sure that some of you, when you were children, went to the beach, either in Texas or maybe on one of the coasts, or maybe in your home country if you're not from around here. And at some point might have picked up a seashell. And you know how when you're a kid and you pick up a seashell, you have the sensation of being able to hear the ocean inside of the shell. Which is really just the air bouncing around inside of the shell. But, you know, as a kid, you convince yourself that there's a boundless world inside of that shell. And that boundless world, that's the kind of thing that this video is about. So I want you to look at this integral here, the integral from 0 to 4 of dx over x squared. Now, we've been talking about improper integrals, and you might look at that and wonder what could possibly be improper about that. But when you graph the function 1 over x squared in the coordinate plane, as I've done here, you notice that as x goes to 0, f of x goes towards infinity. It is boundless, just like the world inside of that shell. So the question is, can I make sense of an integral like this, the integral from 0 to 4 of 1 over x squared dx? And if so, would that integral be finite or infinite? So we're going to approach this the same way that we approached the integrals in the last video, which is because we don't really know how to make sense immediately of an integral where one of the limits of integration is a place where this function is discontinuous, where it's in fact undefined. We are going to treat this limit, or this integral, sorry, spoiler alert, as the limit as a goes to 0 from the right of integral from a to 4 of dx over x squared. All right, so graphically what that means is I am picking an integral, picking a left bound of integration a, and then calculating that integral and letting a go towards 0 from the right. And if that limit exists, if this limit exists and is finite, well, really, if a limit exists in my parlance, it is finite. That's a redundancy there. But if the limit exists, then that's what we declare this improper integral to be equal to. And if the limit doesn't exist, we say that this integral is divergent. So let's find out what happens. This is now a problem that we know how to manage. So let's calculate this. This is the limit as a goes to 0 from the right of, let's see, this is going to be negative x to the minus 1. Evaluated at a and 4 and subtracted. And that's the limit as a goes to 0 from the right. Let me neaten that up a little bit there. Limit as a goes to 0 from the right of, let's see, that's negative 1/4. I think that's a plus 1 over a. There we go. So just going to simplify a bit. Not a whole lot I can do with this, really. That's the limit as a goes to 0 from the right of 1 over a minus 1/4. And as usual, the 1/4, that's just constant. It's not going to do anything as a goes to 0. But as a goes to 0, this is going to do quite a bit. As a goes to 0, this denominator gets extremely small, which means the value of this fraction gets extremely large. It grows large without bound, which means this limit doesn't exist. Doesn't exist. I could also, if I wanted to, I could write, let me move over a bit here, I could write equals plus infinity, because sometimes we write that. Not that we're saying that the limit exists and equals infinity, it just means that the limit grows without bound, and it grows positive without bound. One thing that I don't like, by the way, this is a bit of a digression, but I don't like it when students right at the end of one of these calculations that a limit equals d and e. There's no such thing as equals d and e. That's saying equals does not exist. That's like two consecutive verbs. And not only does it not make grammatical sense, it sounds like you're saying that the limit equals something that doesn't exist, which is just silly. So don't write that. Write either this or this. This tends to be a little bit more informative if it is true. In this case, it is true that the limit is going to positive infinity. Anyway, that was a bit of a tangent there. But what that means about this integral here is that as I let a head towards 0 from the right, as a gets closer and closer to 0, this area here grows bigger and bigger, and in fact it grows without bound. There's no bound on how large this area will get as a gets close to 0. If you ask me to make this integral here, this area, equal to, say, 1,000,000, then I could set a to be something really close to 0, not 0 itself, but something very close, and I could make that area 1,000,000 if I wanted to. I could make it 1,000,000,000,000 if I wanted to. There is no limit on how big that area can be, and therefore we say that the improper integral diverges to infinity. All right, that's one example. Let's do one more. These are fun. Okay, this time suppose I write down the integral from 0 to 4 of dx over square root of x. Okay, so this time my graph is going to look something like this. Let's see here. So that's the graph of f of x equals 1 over square root of x. And again, as x gets close to 0, let's go ahead and label that, thank you. As x gets close to 0, this quantity here, the denominator is growing very small, which means this quantity is growing extremely large. So again, I'm going to have an asymptote at 0, and as x gets very large, this function is going to, well, it's getting kind of messy here, it's going to converge towards 0. There we go. In fact, you'll notice that my sketches of this graph and the other graph there's pretty much no discernible difference between them, and that is because without actually drawing scales on the axes, I don't know how to make them look that much different. But I assure you that there is a significant difference between the two. So let's try evaluating this integral and see whether it's convergent or divergent. That last one, by the way, again was divergent. That was this one. Okay, anyway, so let's try evaluating this one. So again, I set up the integral from 0 to 4 of dx over square root of x as the limit as a goes to 0 from the right of the integral from 0 to from a to 4 of dx over square root of x. And again, the reason I do that, the reason I focus on letting a go to 0 is because I know that this function is discontinuous. There we go, at x equals 0. So when you do an improper integration problem, it's good manners to let the reader know, first of all, that it is improper, second, why it's improper, and then how you're going to represent this improper integral as a limit. That step is absolutely necessary. Anyway, this will be the limit as a goes to 0 from the right. And then taking the antiderivative, I think I get, again, I'm just remembering this from last time, 2 square root of x, the difference in that function's value between 4 and a. So that's the limit as a goes to 0 from the right of 2 square root of 4 minus 2 square root of a. And then that's the limit as a goes to 0 of, I think that's just 4 minus 2 root a. Now think about that one for a minute. As a goes to 0, I know that square roots are always a little dicey, but as a goes to 0, this thing is always defined because a is positive and a is getting extremely small. That means this little term here is going to converge to 0. That means the entire limit here is just 4. So what that means is that if I were to mark off some proper integral inside of this from a to 4, and then think about that area, if I let a go to 0, then this area, it's going to get bigger and bigger. There's no questioning that. But it's only going to get so much bigger. The biggest that area is ever going to get is going to be 4, which is kind of wild. I mean, I drew two graphs, both of which you have to admit look an awful lot alike. They're not, in fact, alike. But this one here has infinite area if you let a go to 0, and this one has a very finite area. That area is 4. So anyway, we call this integral convergent, and in fact it converges to 4. So in the next section we're going to learn a little bit about how to tell whether an integral is going to be, an improper integral is going to be convergent or divergent. And in fact, we will be able to do that in some cases, even when we can't directly evaluate the integral, which is pretty cool. Anyway, that's it for this lesson. I will see you in class. Thank you.